We are progressing through rotational motion, and we've been developing analogs for, I should say, rotational analogs for linear quantities. Like we had a linear displacement, delta x. We figured out that there's an angular displacement, delta theta, that works just as well. We had angular velocities, angular accelerations. Then we started talking about torques, which play the role of angular forces. That's not really a thing. No one says that, but it's how we all think about it. Usually, it's an influence that tends to produce a rotational motion. So we're moving forward. We're basically trying to get rotational analogs of all the tools we have developed, or at least most of the tools we've developed so far. We already have kinematics. Now we're sort of closing in on Newton's second law, the idea of a torque being an angular force. Probably shows you where we're going. We're heading towards Newton's second law for rotating systems. So to do that, first we've got to talk about the rotational analog of mass. And it might surprise you to learn that mass has a rotational analog. But if you've ever swung anything like a baseball bat or a golf club or a softball bat, imagine yourself doing that and imagine what it feels like, and then flip it around. Grab the barrel of the baseball or softball bat, grab the head of the golf club, and swing it. It feels completely different. Why? Because the geometry of the object is different. The mass is distributed in non-symmetrical ways. And so if you were to throw one of those things, don't throw your golf clubs, right? No matter how bad you shank your shot, don't throw your golf clubs. But if you do, they rotate strangely, right? You can see it. I mean, they don't rotate nice and smoothly. They might turn smoothly, but they're rotating about a point that's not in the center. Turns out they're rotating about the center of mass. But that all kind of plays into this idea that the way the mass is distributed in an object plays a role in determining how it rotates after a torque is applied. So what we're talking about, the rotational analog of mass, is called the moment of inertia. And in general, it is a quantity that takes into calculation both the mass of the object and the geometry, similarly to how a torque took into account the force applied to an object and the location of the force and the geometry of the object. We're taking into account the geometry and the mass here. Units of moments of inertia are kilogram square meters. The meter squared takes care of the geometry here. The kilogram will take care of the mass. The full treatment of this tells us this. Moment of inertia, which we use to symbolize I, is equal to the integral of this quantity, r squared dm. So what in the world do we mean by dm? So if you have been through Calculus 1, if you're in my course here at Auburn, you have been through Calculus 1. But if you have, and you haven't been much farther, like you haven't been through Cal 3, the dm might just really throw you right now, because dm is a differential mass element. How in the world do I do that? Well, I take an object, and then I'm going to cut out a little piece of it, right? And I'm going to let that little piece, which has some mass, shrink down to a differential. So I take a delta m, some mass that is in this little area, or a little volume, or a little line, whatever, and let that shrink down to a differential mass element. Now, of course, the integral of dm is just m. If I integrate over the whole dm of this thing, I just get the mass of that object. So that's all well and good, but explicit calculation of this is often a little bit interesting. And if you've never seen before, it's really, really interesting. Because we know how to integrate over space, right? A dx, you give me a dx or a dy or a dz, and I am good. We don't usually think about until we've taken some more advanced mathematics how to turn something like this into something involving a spatial variable over which we can integrate. To show you what I mean, let me take a really thin wire. Now this wire has some length L and some mass M. And of course, this wire has a volume, right? It's got a little bitty radius, and if I really, really wanted to, I could measure that radius, and I could determine the volume of this, just model it as a cylinder. But if it's thin enough that that doesn't bother me, I can kind of just forget about the volumetric nature of this and model it as just a line, right? I know it has a volume, but I'm going to model it as a line. And so it's a line of length L, I guess that makes it a line segment, and mass M. Okay, what I can do now, assuming that this mass is uniformly distributed, right? There's one end of the wire is not bigger than the other end, it's just nice and straight. Assuming that's all that's the case, I can form what's called the linear mass density. We use a symbol lambda, which is the Greek L, for linear. Linear mass density, which I'm going to define as the mass just divided by the length. It's the mass per unit length. And so if this is 1 kilogram and 1 meter long, I get a mass density of 1 kilogram per meter. And that's the units tell you something, right? Kilogram per meter. It means in every meter of this thing, I get this much mass. I should say, this many kilograms. So this is the linear mass density. We can form area densities. Most often we form volume densities, and if you've seen densities before, that's probably what you've dealt with. But this linear mass density is also useful to us. Densities are frequently useful to us in how we rearrange this definition. So notice, if I know the linear mass density of some substance, which I make wires out of, and somebody cuts off a certain length of wire and they want to know how much mass is in there, I can just rearrange this equation. If I know the linear mass density, if I buy a spool of wire and it says linear mass density such and such kilograms per meter, and then I cut off, 6 meters of that, and I want to know how much mass I have, I just do this simple calculation. The density times the length gets me the mass. All right. Well, I'm going to use this to see if I can turn this dm into something spatial over which I can integrate. I always need to turn this into a spatial variable. So let's look at this m is equal to lambda L. Let me form a differential on both sides of this. dm is equal to let's do this, lambda L, but lambda is a constant. Notice the mass and the length are both constants. I can pull it out. This is going to mean dm, my differential mass element, I'm taking a limit on either side, is equal to lambda dl. Okay, now, fair enough. It looks like I'm getting closer to something that I can integrate. What is dl? Well, dl is going to be a placeholder now for whatever spatial variable I'm comfortable with. For this horizontal line, dl is probably going to get turned into a dx, right? dl is just a placeholder. If my line were vertical, dl would probably get turned into a dy. So I've actually solved my problem. I've taken this dm that I don't really know what to do with, and I've expressed it in terms of something physical and a spatial variable that I'm happy to integrate over. All right, let's see it in action. Let me take a bar, and I'm going to assume that this bar is thin enough so that I don't have to worry about the volume. It's length L and mass M. So same thing. Say that I'm going to say that the linear mass density is equal to M over L, which are parameters that I know. And I now know how to express dm. And I want to know what the moment of inertia is of this bar. Now, of course, as soon as I say that, I've got to ask the same question I asked with torque. About which point? Right? The moment of inertia about the center is going to be different than it is about an end. If you grasp this bar in the center and you try to rotate it, right, you just sort of rotate it around, it's going to feel a certain way. But then if you go over and you grasp it at the end and you rotate it around, it's going to feel different. Because the way the mass is distributed away from that point is different for every point. And so if I'm going to say the moment of inertia of this object, I've got to say the moment of inertia about some point. So let's pick out this point here, the end. The idea, if you need something physical to visualize, you're going to pin it at the end with a hinge and allow this thing to rotate about the end. You don't have to do that if you don't need to, but if that gives you something to think about. So, okay, I need more paper. How do I calculate that? Well, first of all, I'm going to set up a coordinate system. I'm probably going to put my origin over here, where my point of summation is, which means then I'm going to set up my integral as a definite integral from this point, which I'm going to call 0, to this point, which is a length L away from 0. I might as well call that L. Of this r squared dm. Now, let me take these general placeholding variables and turn them into my specific variables. This is horizontal. That invites me to use x, right? What is r? R is the distance between my particular dm that I'm evaluating right now and the origin. So if I'm going to use x here, my r is going to become an x. This is r is general, x is specific to my case. And my dl up here, when I plug in dm, is going to become a dx. Again, if this were vertical, they probably would both become y, but it doesn't matter. It's just a name. What matters is how we handle it. So let me go ahead and make those changes, 0 to L, of instead of r, I'm going to write x, because that's the variable I want to use, x squared, times dm, but I'm going to write lambda dx for dm. That's my dm. So r squared dm, which is my general way of writing it, has become x squared lambda dx. All right, if we're okay there, we keep on moving. Get this to where you can see it and I can write on it. That means the moment of inertia about the end here is going to be, I'm going to pull out the lambda. I'm going to get integral of x squared dx, which is going to be x cubed over 3 dx, right? And then I'm going to evaluate this. Good grief, there's no dx anymore. Sorry. Let me do that again. The moment of inertia after I evaluate this is going to be lambda, which I pull out of the integral. It's a constant. The integral of x squared dx is x cubed over 3. No dx. I'm not sure where that came from. Evaluated from 0 to L. And what I'm going to get here, at the lower limit, I'm going to get 0. At the upper limit, I'm going to get L. So I'm going to get lambda L cubed over 3.